Welcome SY-based students. Today we are going to discuss about complex variables. Unit 3rd, complex integration, Lorentz theorem. Let fz be analytic on two concentric circles C1 and C2, and also in the ring shaped region it is analytic on this C1 and C2, also on the ring shaped region bounded by these circles. Let z is equal to a be the center of these circles. R1 and R2 be their radii respectively such that R1 greater than R2, then for any point z of the region R bounded by C1 and C2, we have fz is equal to summation n goes from 0 to infinity an in bracket z minus a raised to n plus summation n goes from 1 to infinity bn upon z minus a in bracket z minus a raised to n. Suppose this is equation 1 where an is equal to 1 upon 2 pi I integration over c1 fz upon z minus a raised to n plus 1 dz for en is equal to 0, 1, 2, 3 up to infinitely, and bn is equal to 1 upon 2 pi I integration over c2 in bracket z minus a raised to n minus 1 fz dz for en goes from 1 to infinitely. The ring shaped region are bounded by C1 and C2 is also called an annulus. See in figure, this is the annulus. We call it annulus. The series in the RHS of 1 is called Lorentz series of fz at about z is equal to a. Remark, in the Lorentz theorem, if fz is analytic inside C2, then z minus a raised to n minus 1 fz is also analytic inside C2. Hence, by Cauchy's theorem, integration over C2 in bracket z minus a raised to n minus 1 fz dz is equal to 0 where n goes from 1 to infinitely. Thus, therefore, bn is equal to 1 upon 2 pi I integration over C2 in bracket z minus a raised to n minus 1 fz dz is equal to 0 for en goes from 1 to infinity. Thus, each bn in Lorentz series vanishes. Hence, from equation 1, Lorentz series becomes fz is equal to summation n goes from 0 to infinity, which is a power series and hence Taylor series. Power series means Taylor series. Thus, Taylor series in particular case of Lorentz series in which no negative powers of z minus a in bracket z minus a occurs. Example, expand fz is equal to 1 upon z minus 2 in Lorentz series valid for modulus z greater than 2. Solution, when modulus z greater than 2, therefore 1 upon modulus z less than 1 half, or modulus 2 upon z less than 1. Therefore, we express these in the 2 upon z form. Therefore, take outside the bracket in the denominator z. Therefore, fz is equal to 1 upon z minus 2. Take outside z. Therefore, 1 upon z. 1 upon 1 minus 2 upon z. When we multiply by z this bracket, z minus 2 again we get z minus 2 is equal to 1 upon z summation n goes from 0 to infinity 2 upon n raised to n as in bracket 2 upon z raised to n as modulus of 2 upon z less than 1 is equal to n goes from 0 to infinity. Here z we put in the summation Therefore, we get 2 raised to n as it is z raised to n and z that is z raised to n plus 1. Modulus 2 upon z less than 1. Thus, fz is equal to summation n goes from 0 to infinity 2 raised to n upon z raised to n plus 1 modulus z less than 2. Next example, expand fz is equal to z square minus 4 upon z square plus 5z plus 4 in powers of z for 1 modulus z less than 1, second 1 less than modulus z less than 4, and third modulus z greater than 4.